So today I will show you how to check deflection for slabs or beams on ETABS. So here are two diagrams. One is my original axis of beam, another one is elastic curve. Elastic curve, or it is nothing but deflected shape of beam. Deflected shape of beam is also called as elastic curve. So deflection, it is nothing but the vertical distance between original axis of beam to deflected shape or elastic curve. So deflection, it is defined as the vertical distance. So this distance, the vertical distance between original axis of the beam to deflected shape. So this vertical distance, we call it as deflection. So deflection, it is denoted as delta, and it will be always measured in millimeters. So deflection depends upon, one is external load, that is P, or sometimes it is W. Span of the beam, or slab, so which is L, length of the beam or slab. Next, cross section of beam, so it may be width and depth. In case of slabs, it is thickness. And deflection, it also depends on modulus of elasticity. Modulus of elasticity, so or Young's modulus, it is nothing but your type of material, whether it may be concrete, steel, wood, or pre-stressed concrete, because different materials will have different modulus of elasticity. So next factor will be support condition. Support condition or boundary condition, whether the beam is simply supported or fixed. Okay, so deflection depends on factors like external load, span of the beam, cross section of beam, modulus of elasticity, and support condition. So you can refer SP 16. So in table number 98, deflection formula for prismatic beams. See, here you have simply supported beam with the central point load. So deflection formula will be PL cube divided by 48 EI. So the condition is simply supported beam carrying point load exactly at center. So this total span is L, whereas this will be L by 2. So in this case, deflection equals P L cube divided by 48 EI. Yes, PL cube divided by 48 EI. So here deflection, it is depends upon external load, length of the beam, and type of material. Type of material is Young's modulus. Here I means moment of inertia. Again, for rectangular section it is BD cube divided by 12. Again, moment of inertia means it depends on cross sectional area. So if you refer IS 456 2000 clause 23.2 page number 37. So you have criteria for control of deflection. So let me open IS 456 on page number 37. Yes, clause 23.2 control of deflection. See, you have two criteria. First is the final deflection due to all loads including the effects of temperature, creep and shrinkage, and measured from the as cast level of supports of floors, roofs and all other horizontal members should not normally exceed span by 250. So first criteria is span divided by 250. It is without partition. Without partitions or finishes. So you have second criteria, the deflection including the effects of temperature, creep, shrinkage occurring after erection of partitions and the application of finishes should not normally exceed span by 350 or 20 mm, whichever is less. So second criteria it will be, so L by 350 or 20 mm. So it is L by 350 for with partitions and finishes, with the partition load and finish loads. So span by 350 or 20 mm. Again it is whichever is lesser. So this is as per IS 456-2000 class 23.2 page number 37. So these limits are for permissible deflection or allowable deflection. Allowable deflection. So you should remember, while checking the deflection, we always check deflection with respect to shorter span of the slab, and deflection check it is service limit state. Service limit state, which means dead load plus live load. You should remember these 2 points. Again, this is also stated in IS 456. I think it is in the beginning only. I forgot the clause number. Yes. So table 18. So limit state of collapse and limit state of serviceability. So for limit state of serviceability, partial safety factors are 1. So DL times 1, this is live load, dead load and live load with factor of safety 1. To understand this deflection check, I will take you to ETABS and I will create a simple model. So here I will explain this model. So column sizes are 300 by 300 millimeter, and beam sizes are 200 into 450 mm. Okay, so this span is 6 meter, whereas this vertical span it is 8 meter. This is 8 meter. And the thickness of slab, so thickness of slab is 150 mm, and I will use load, dead load as 1.5 kilonewton per meter square, and live load as 2 kilonewton per meter square, and I use mesh size as 0.3 into 0.3 meter. It is a square shape, so 0.3 into 0.3. Okay. Floor height, it is 3 meter, and I use FCK grade of concrete as M20, and grade of steel as 500. Okay, so let me model the same. So open ETABS. First select new model. So select the units here, metric SI, Indian, IS 800, IS 456. Click on OK. So it will ask you for number of stories. So number of stories, 1. Story height, I will define it as 3 meter. You click on custom grid spacing, edit grids. So select display grid data as spacing. So first, number of grids in X direction. Yeah, you have 2 grids. Number of grids in Y direction, you have 2. Spacing grids in X direction. So as per the model, it is 6 meter in X direction and 8 meter along Y direction. So 6 meter along X direction and 8 meter along Y direction. Clear? I will decrease the bubble size. Click on OK. Yes, you just close the 3D view. So go to plan, base, first you create material property. So add new material, Indian concrete. So grade of concrete, it is M20. So M20, density of concrete here, it is 25. Okay. Next, add new material. So in case of rebar, you use HYST grade 500. So density, I think 78. Okay. Next, define section property. So your column sizes are 300 by 300. Add new property, concrete. So column 300 into 300. So grade of concrete, it is M20. So depth 300, width 300. So modify, I will use the stiffness modification factors as 1, and reinforcement. So longitudinal bars HYST 500, confinement, which means stirrups, HYST 400. So I am design type, I will design this as column. So axial load MU2, moment along 2 direction. So for columns clear cover, it is 3, number of longitudinal bars along third face 3, number of longitudinal bars along the second direction face. I will use 3, equal distribution. So I will use 16 mm dia bars. So for stirrups I will use 8 mm. Okay, so this is my column 300 into 300. Next, add new property. I will create beam. What is the beam size? 200 into 450 mm. So depth of the beam 450, width 200. Stiffness modification factors 1. So design type beam, HYST 500, HYST 500. Cover to longitudinal rebar group centroid. So it will be, I will change this to 40. Okay. Okay. So you created beam and column property. Next you create slab. Define section property, slab section, add new property. So slab thickness 150 mm, grade of concrete M20. So here modeling type shell thin, thickness 150 mm. So I will check the beam property whether I have changed the grade of concrete. Sorry, for beams grade of concrete it is M20. Okay, okay. So once you define material properties and section properties, now you are ready for modeling. So go to plan, select story 1. So first model your columns. So first model your columns. So column size is 300 by 300. So first column, second column, third column, fourth. Okay. Next, model your beams. So beam types, beam type, you have beam 200 into 450. So from here to here, first beam, this is your second beam, third and fourth. Okay. Next, model your slabs. So slab property, it is S150. Yes, so this is your model. Go to plan and base. You select all the 4 joints and you change the joint restraint to fixed. Apply. OK. So I will change this font size. Options, graphic preference. So instead of 8 I will use 12. So this horizontal span it is 6 meter and this vertical span it is 8 meter. So I will switch on the beam property. Beam size 200 into 450, slab 150 mm. So you assign load. So what is the load you considered? Dead load 1.5, live load 2. So you select the slab, go to assign, shell loads, uniform, dead load. So dead load it is 1.5. 1.5, apply. See here. So dead load 1.5. So I will remove the section property. See, dead load it is 1.5. You select the same slab, and under live load, what is the live load? It is 2. See here, if you just right click on this slab, you check the loads. Dead load 1.5 kilonewton per meter square, live load 2 kilonewton per meter square. Next remaining part is the meshing. So you select the slab, go to analyze, automatic mesh settings for floors. Here use a rectangular mesh. So mesh size it is 0.3. Okay. So go to define load combinations, add new load combination. So load combination is dead load plus live load. So combination type it should be linear add, dead load scale factor 1 add, and live load scale factor 1. Okay. You run the analysis, it will ask you to save. You save it in the file name as deflection check model. Deflection check model. Yes. So go to display, deformed shape. In combination, you select dead load plus live load. So contour options. So here X and Y are perpendicular. So out of plane will be Z. So draw contours on object. Show contours for UZ. So it is gravity direction. So apply. Okay. See here. So this is the deflected shape. So maximum deflection it is minus 19.5. Deflection it is in minus 19.5. You just observe this contour. This magenta color, it represents higher deflection, and this blue color region it is very low deflection. So in your model, where you will have the maximum deflection at the center, so this is in magenta color. Where you will have the very low deflection at the supports, at the corners, you have very low deflection. Either you can view this by 3D. See here. So deflection will be maximum at the center and very low at the column corners. Okay, so go to plan. So maximum deflection, I think it is 19 point. You just use your cursor and place it on any node, you will get UZ value. So maximum deflection it is minus 19.76. See here. So in this model, your ETABS deflection, it is 19.76 millimeter. Clear? Or it is your actual deflection for service loads, which is for dead load plus live load combination. So ETABS deflection is 19.76 mm. What is the allowable or permissible deflection? Permissible deflection is, so as per code, it is L divided by 350, span divided by 350. Clear? So here span is, it is always shorter span. So for which shorter span is 6 meter. So which is 6000 millimeter divided by 350. So 6000 divided by 350. So it will be 17.14 mm. 17.14 millimeter. So your permissible deflection. You just compare your actual deflection and permissible deflection values. So in this case, actual deflection is greater than allowable deflection. So if you compare these two values, your actual deflection, it is 19.76, which is greater than allowable deflection or permissible deflection. It is 17.14. So we can say that slab is failed in deflection check. Slab is failed in deflection check because your allowable deflection is 17 millimeter, but your actual deflection is 19 millimeter. Okay, so we can say that slab is failed in deflection check. So now what is the solution? What is the solution? You have many types. So in those I will discuss one or two methods. First solution is increase thickness of slab. Increase thickness of slab. So initially I used the thickness of slab as 150 mm. Now I will use the thickness of slab as 200 millimeter. So I will go to my ETABS model and I will change the slab thickness. So go to define section property, slab section. So instead of S150, you define new property. So it is S200, slab 200 mm thickness, grade of concrete, it is M20. So modeling type, let it be shell thin. So thickness, it is 200 mm. Okay. You select this slab, go to assign shell slab section. You assign a slab section of 200 mm thickness. Apply. Okay. Now thickness of the slab, it has been changed to 200 mm. Now I will run the analysis. So run the analysis. So go to display, deformed shape, your combination, it should be dead load plus live load. We check the deflection for service limit state. So our service limit state will be dead load plus live load. So apply. Okay. So if you see the deflection, now it is around 15.28. You just click on this node. Click on this node. I think it is 15.28. So when you change the thickness of slab to 200 millimeter, so your actual deflection so it will be 15.28 millimeter. So what is your permissible deflection is, again it is same, span divided by 350. So again it is 6000 divided by 350. It is again 17.14 millimeter. So now you compare these two values, actual deflection and permissible deflection. So in this case actual deflection is less than permissible deflection. So your actual deflection is 15.28 millimeter, which is less than your permissible deflection is 17.14. So hence it is okay. So as long as your actual deflection should be less than permissible deflection. So this is the first solution, by increasing the thickness of slab. So second solution is, so this is first solution. Second solution is increase number of elements. So which means increase number of beams or columns. Okay. In the same model, I will introduce two new columns. So I will introduce one column here and I will introduce one column here, same column size. So 300 into 300. So this is also same, 300 into 300. I will divide this span. Initially it was 8 meter. So now I will introduce a column at the center. I will divide this span to 4 meter and this span 4 meter. So I will take you to your ETABS model. So display undeformed shape. You unlock your model. So click on create column. Column size is 300 into 300. So you go to draw, snap objects. You turn on this line edges and midpoints. Then only you can track your midpoint. Yes, this is your midpoint. You just insert a column here. Again at this midpoint you insert a column here. So now I increased the number of elements. Initially I had only 4 columns. Now it has been increased to 6 columns. Now you run the analysis. So go to display, deformed shape, combination. You should ensure dead load plus live load. Show contours for along Z direction. Apply. OK. See here. Now the deflection it is decreased to I think 5.2 or 5.54. So in this case actual deflection it is 5.54 millimeter, whereas your allowable deflection it is 17.14 millimeter. Again you compare these two values. So your actual deflection which is much more less than your allowable deflection, because actual deflection is only 5.54 mm. Your allowable deflection is 17.14 millimeter. So now you can comment slab is safe in deflection check. Slab is safe in deflection check. Okay. So being a structural engineer, you should select correct way of checking. So my first solution is increase slab thickness, and second solution is increase number of elements. So when I increase slab thickness to 200 mm, my actual deflection is 15. So when I increase number of elements, which means I introduce 2 new columns, my actual deflection is 5.54 mm.